Okay, so thanks for bearing with that interruption to get set up again. But we're going to jump back into slides from chapter 12. I've also posted the chapter 13 slides to the file section on Canvas, and we're going to try to get into that today. That's what we're scheduled for, but I want to give enough time for all of the content. We will be skipping some of the material in chapter 13 because it's, in my opinion, something that you either will learn or have learned in chemistry. So things like reaction energies, catalysts, those sorts of ideas. If you're interested in getting a more physicsy understanding of them, then you can definitely read those sections of the textbook. It would only benefit you, but I'm not going to quiz you on how catalysts work in this class. Okay, and just a reminder, we will have a quiz tomorrow, and then the homework will be due Friday night. So make sure you're working on the homework and that you're, preparing for the quiz. The quiz will be on something related to heat transfer, some combination of like heat transfer and the MCAT stuff, maybe some calorimetry type ideas. Did your TAs go over calorimetry yesterday? A little bit? No? Maybe. Like looking at how if you have like some ice cubes in a cup of water, what temperature does the whole system come to equilibrium at? Okay, so maybe some did and some didn't. But we can, I'll potentially send out a review of that or something for the people who had less exposure to it. Okay, but anyway, so yesterday we were talking about ideal gases as an example system in thermodynamics. So we can use the tools of thermodynamics, ideas like work and heat and temperature, to study a whole host of systems. You can look at, not only liquids, gases, solids, but also you can look at magnetism. You can even look at surface tension from the lens of thermodynamics, using these same tools and ideas. But ideal gases are nice because we have what's called their state equation, right? The ideal gas law, PV equals nRT, tells us how the state variables, the macroscopic variables, pressure, volume, temperature, are related to each other. And so we can just make a lot more progress with ideal gases in terms of writing things down than we can with other systems. So in general, for a gas, not just ideal gases, the work done is basically the area under this PV diagram. So the top left example is when we change the volume of a gas. So we let a gas push on something, expand. And so that is going to do work. That's going to turn the energy of the gas into some force, some motion that's actually able to transmit energy, right? So you could imagine in a car engine, the heated gas after combustion pushes on the piston. So its volume is changing, it's doing work, and that's what allows your car to move forward. So it's a force over a distance. And so to calculate that amount of work, we would start at some initial volume, we end at some final volume, and we find this area. And so you don't need calculus to do this example because it's just a rectangle, right? So the work here would just be negative PV for this isobaric or constant pressure system. And remember, we can always write down PV equals nRT for these things. In all of these examples, N is assumed constant. And so if we're holding pressure constant, then when volume changes, temperature will also change. So just be aware of that when we allow a gas to expand, it's going to cool down, basically. And when we compress it, it'll heat up. Okay, so then in the isochoric situation, which is actually similar to what the gas was doing in this boiling flask in the demo, the volume is being held constant, but the pressure is changing, right? We added the dry ice on top and the pressure dropped, but that doesn't do any work. It doesn't have any ability to transmit energy to something. Like you can't throw a baseball with gas that's not allowed to change the size of its container, right? Even though the pressure is changing, it's not able to exhibit this idea of work. And so we can see that in that the area under this curve is 0. It's just a straight line. And then the other two situations are a little bit more complex. So I just want to talk again about how we can make these happen physically. So if we have some system, and again, I still having pin troubles, and we hold the temperature constant in that system, usually by surrounding it with like a water bath or something. So if I want to hold the temperature of a system at 70 Celsius, I would just put it in a box and surround it by a bigger box of water at 70 degrees Celsius. That will cause an isothermal process, so a constant temperature. And so you can see if temperature is constant in the ideal gas law, then pressure is related to 1 over volume. So it's like a y = 1 over x type of equation. And so if you've taken calculus, if you integrate y = 1 over x, you'll get a logarithm. And so we do expect you to be able to use this formula, although you don't have to derive it in the class and you don't have to memorize it. It'll be available to you. But basically, this allows you to find how much work is done on a gas in the process of its volume and pressure changing together, with the idea that we're holding it at a constant temperature. Okay, so like I said, that usually is done by having a big thing of that temperature surrounding it. Like water is a great example because it has a high specific heat capacity. And then a similar but a little bit different idea that comes up in these thermodynamic situations is adiabatic. And this is where the heat in the system is constant. So basically what this means is that we're not adding or subtracting thermal energy from heat, but we can add or subtract thermal energy from work in these situations. And you can see that because there's some area under this diagram. So there's a potential for work in an adiabatic process. And the way that you would make one of these happen is you would surround your system with an insulating material. Okay, so if you surround your system with an insulating material, it's unable to give energy thermally to its surroundings. And so the only thing it can do to change its internal energy is work, right? Remember from the first law of thermodynamics, internal energy is work plus heat, or change in internal energy is work plus heat. So if a adiabatic system wants to change its internal energy, which remember, this is the thing that's related to temperature, then it has to have some work either done on it or done by it. And so these are the 4 primary types of systems you'll encounter. The only really thing I expect you to know about adiabatic systems is to know what they are, constant heat, so insulated, and to know that the curve of an adiabatic system is steeper than the curve of an isothermal system. Okay, so what that means is that if you want to go from one point, one pressure and volume, to a different pressure and volume, usually the most efficient way to do that is with an adiabatic curve. Okay, so just to write that out, if this is our PV diagram, let's say that for some reason I'm an engineer and I want a system to go from this pressure and volume to this pressure and volume. You can imagine somehow making this process a straight line, but that would involve like some complex set of valves and releasing and gaining pressure at the right times, right? Making things a straight line on a PV diagram is very hard. So usually you'll only have these 4 tools at your disposal. So you could, so you wouldn't be able to make this straight line, but you could do an isochoric process and then an isobaric process. And so that would have this whole area as the work required. Or alternatively, you could do an isothermal process, right? Putting it in a vat of something at a constant temperature. That would give you this line. But what I want you to understand is that the most efficient line in most cases, certainly relative to isothermic, is this adiabatic process. So this adiabatic process is going to be very steep and a very quick connection that requires the least work, basically. But you won't be expected to actually calculate the work done by these because it's a little bit more annoying and it's not in the textbook. So I didn't think it was fair to ask you about. But are there any questions about how work is done on or by ideal gases when we're keeping one or more things constant? Yeah.
Is work always going to be negative if you're doing work on something else?
So this is a very good question. So there's a negative sign in this PV diagram, but remember, if you or sorry, maybe not remember, if you've taken calculus, you'll know that integrating from left to right gives you a positive thing, right to left gives you a negative. So it's the same idea here. So if you don't know calculus, what you should know is that if I have some curve on my PV diagram, if I'm finding this area, if I think about going this way along the diagram, so from a low pressure, from a low volume to a high volume, then this is going to be a positive area. And so the work, since it has a minus sign in it, will be negative. So this will be negative work. However, if I have that same curve, but I go the opposite way, then this is a negative volume, but because the work equation already has a minus sign in it, this would be positive work. And the work equation here, the negative P delta V thing, is actually telling you the work done on the gas. Okay, so when we say that there's negative work, that's telling you that, so you can see that's the case where we're going from a small volume to a large volume. So that's telling you that the gas is losing energy to work, negative. And so in the opposite case, we're going from a big volume to a small volume, we're compressing it. That's telling you that the gas is gaining energy from work, and that would be the positive case. So I'm really glad you asked that. The plus and minus signs can be quite tricky in these situations. And so if you're having trouble with this, I would encourage you to read through section 12.7 of the book. It's really helpful just to see it written out and maybe to take it at your own pace, because I'm trying to tell you the details, but also go reasonably fast so we can get to everything we need to get to today. So very good question. Any other questions about these? I think this is one of the trickier things in this part of the course, so it's good to talk about. Okay, so then still thinking about ideal gases, there's something else that we need to figure out if we want to really understand their thermodynamics, which is their heat capacities. And these are all molar heat capacities. So these are all joules per mole Kelvin. That's the units in this table. And what you'll notice is that there are a lot of the same numbers, right? And whenever you're a physicist and you start to see a lot of the same number somewhere, that's a pattern, a very basic pattern. And it's a great hint that there's something going on that's worth understanding. And so this is covered in section 12.7 of the book, but it also is one of the main topics in chapter 13, is understanding why is it that gases have heat capacities that when you think about them in terms of moles are very similar. Now remember, gases have different, molar weights. So if you convert these into joules per kilogram Kelvin, then this pattern goes away. You'll just be like, look at all these random numbers. But when you think about them in terms of moles, there's a very nice relationship. And I just want to highlight that there are two primary types of heat capacity for gases. So if you hold a gas at a constant volume, you put a gas in a box or in the top of this boiling flask, then that gas will have a heat capacity, which is the C sub V, which is the constant volume heat capacity. So C sub V, this is for a constant volume process. However, if instead you have a box that can expand, so a balloon is an approximate example, but the pressure in a balloon actually changes because of the stretchiness of the rubber, so it's kind of complex. But if you had a box with a piston in it that could expand as it needed to, such that it would keep the same 1 atmosphere of pressure. You have 1 atmosphere pushing up on the piston from the outside, and then no matter what you do to the gas inside, it would just move this wall of the container such that the volume would change, but the pressure inside would stay constant. that would be a constant pressure process. And it would have a different heat capacity. And it turns out that the constant pressure heat capacity is always bigger than the constant volume heat capacity. And that's because when you allow the volume to change, that's work, right? And so as you add heat to an object, to this gas, if you're keeping the volume constant, all of that heat is going into changing the temperature. All of that heat is going into internal energy. But if you allow the volume of the gas to change and you add some heat to it, you put a flame under it, some of that energy will go into temperature, but some of it will go into the expanding the gas, which also takes away some energy. So that's why the temperature will then change more slowly if you have the volume able to change, right? It all goes back to these diagrams. For the case where we're at a constant pressure, that's this isobaric, the top left diagram, there is some work there. So if you think about the first law of thermodynamics, when we add heat, some of it goes to work and some of it goes to our thermal energy. Whereas for the isochoric process, the constant volume, so a gas in a box, all of that heat goes into thermal energy because there's no work there. The W is 0. Okay, so that's why CP in this table is always bigger than CV. And in fact, it's bigger by a very nice number. This R here is the ideal gas constant. So 8.31, whatever, joules per mole Kelvin. You can see it even has the right units automatically, which you can check with the ideal gas law that those are the right units. And so then there's a really nice way to figure out what these numbers are. So you can see if I know what CV is, I just add R to it and I'll get CP. And so we have a separate formula to get CV initially. And this is one of the, in my opinion, one of the coolest results of this looking at the molecules, looking at the atomic physics to understand the macroscopic, the big scale physics. Okay, so what happens here is that the gas, let's think about a gas like these Nobel gases that's monatomic under standard conditions. So we have a helium atom and a bunch of its friends, and they're bouncing around. And as they're bouncing, they can move along the x-axis, they can move along the y-axis, they can move along the z-axis. So they have 3 directions in which they can move. And so we say that they have 3 degrees of freedom. That's what this D means. And so all we have to do then is plug that D into this equation, which we'll talk about in chapter 13, why this is the correct expression for the heat capacity of gases. And we see that for a monatomic gas, the constant volume heat capacity is just 3/2 times R. So if you do 3/2 times R, which is 8.3, you'll get 12.5. And when chemists in the late 1800s realized this, they were amazed, incredulous that this was enough to predict these heat capacities. And then you just have to add 8.3 to get these constant pressure heat capacities. You'll notice for the diatomic gases, we have some different numbers. And that's because if you think about a diatomic gas like diatomic nitrogen, which is most of the air in this room, not only can this molecule move in the X direction, the Y direction, and the Z direction, but it can also rotate, right? For a monatomic gas, if it rotates, we can't tell. Atoms just look the same no matter what direction they're in. But for a diatomic gas, if it rotates along its length, we still can't tell. But if it rotates this way or this way, then we do notice. And so basically it has 2 extra degrees of freedom. So it can move X, Y, Z, and it can rotate either in this direction or in this direction. And so the D for diatomic gases is 5. And so if we just plug in 5/2 times R, which is 8.3, then we'll get 20 point something, you know. It starts to break down a little bit as you get to more complex molecules, but it's a good start when we're thinking about these monatomic and diatomic gases. And so it doesn't matter what actually the elements are, it just matters what structures, what molecules they're making with each other. So noble gases will tend to be by themselves monatomic, and then every other gas is going to be diatomic at every other elemental gas is going to be diatomic at standard pressures. Okay, so I know this is a bit confusing. How are we feeling on this? Any questions about how? So just to give you a quick recap, if you are given a gas, like I tell you, I want to know the heat capacity of gaseous iodine or something, then you can ask yourself, is that a noble gas? No, iodine's just a random element. So it's going to be diatomic. And so for a diatomic gas, they can move, they have 5 degrees of freedom, we say. They have 5 directions they can move in, X, Y, and Z, and then they can rotate in 2 different ways that make them look different. And so as a result, the constant volume heat capacity is 5/2R. And then we just have to add an extra factor of R to get the constant pressure heat capacity, which is bigger because that involves all of the heat going into temperature change. Okay. So that's the Cliff Notes version, I guess. But like I said, there's a lot more information in your book that I would encourage you to read because this is a tricky idea. But yes, questions. Mm-hmm. Yes, so let me show you my next slide and I can answer your question. No, very, very good question. Very good question. So it turns out that, so this diagram is for diatomic molecules. It turns out that 5/2, a little bit of approximation. So like you can see here, there's 3, the right-hand side is showing you the 3/2, 5/2, so on. There's 3/2 translational degrees of freedom. So that's just moving side to side. So 1 degree, 2 degrees, 3 degrees, 3 different directions. And then for diatomic molecules, since they're symmetrical, if you rotate them this way, they don't look any different. We only have an extra 2 rotational. They can rotate this way, or they can rotate this way. But you can imagine that the molecule could also oscillate. It could oscillate like this, or it could oscillate like this. And so in reality, there are an extra 2 degrees of freedom in diatomic molecules. And this confused chemists at first because they were like, okay, we've got a great system, monatomic gases, perfect, it works great. Diatomic gases gets a little sketchy, what's going on? And it's basically that in order for these oscillations to start to happen, there's a minimum energy. In the same way that electrons around an atom have like a minimum energy when they're in that s orbital, there's a minimum energy associated with these oscillations. And so if the temperature of the gas isn't hot enough, you won't manage to excite those oscillatory modes of energy. And it turns out that the transition temperatures are dependent on the mass of the gas, basically, and how strong its bond is. And so that's why you get these little differences, because some gases like nitrogen have a really strong bond and are pretty heavy. So they're going to have a larger heat capacity compared to hydrogen, which will have a smaller heat capacity. And we'll talk more about this. It'll make more sense when we get to springs, because these molecular bonds really just act like a spring. And so there's some stiffness associated with them that determines their oscillatory properties and energy. But the moral of the story is for monatomic gases, this works almost perfectly. You can see that it's amazing agreement, 12.5, 12.5, but for diatomic and especially beyond, like water vapor is a triatomic gas. So you would think, well, actually water vapor, maybe it has, well, for water vapor, it still has one rotation axis that's not actually a degree of freedom because it's symmetrical. But for a more complex gas, like some synth, like aromatic compound, it would have more degrees of freedom, but in reality, it often can't excite them. It's not at a high enough temperature. So there's a little bit of difficulty, and this type of analysis does break down beyond diatomic gases. Triatomic and beyond doesn't really work well. You just have to measure it. But for the first monatomic and diatomic gases, works amazingly. As long as you just remember to count the degrees of freedom correctly, ask yourself, do I want the CV or the CP? And remember that these are in joules per mole Kelvin. So you'll often need to convert into joules per kilogram Kelvin or something, depending on your calculation. Okay, and then you can see once we have those heat capacities, we can use these equations, which are the equivalent of the MCAT equation we had before, but now instead of mass, we have a number of moles. So we can do, if you want to find out how much the temperature changes based on some amount of heat that you add, you just divide by the number of moles and the molar heat capacity. Okay, lots of talking here. I think, yeah, we'll get to that in a second. But let's take our halfway break and stretch and talk a little bit so that we can think about these things some more. I'm just gonna play with this. So yeah, we should probably get back into it, but hopefully a little break, good for refreshing. So just to do an example, using these heat capacities. So here we have 3 moles of diatomic oxygen held at 20 degrees Celsius. So N is 3 moles. The temperature is 20 degrees Celsius, so 293 Kelvin. 600 joules of heat are transferred to the gas at constant pressure. So at first, we're going to be at constant pressure with 600 joules of heat. And then 600 joules of heat are removed at constant volume. And they want to find the final temperature here. So this is a great example to show how keeping a gas at a constant volume is really different from keeping it at a constant pressure. And just by thinking about energy and heat, we don't get the full story, because remember that the change in thermal energy is from the work plus the heat. And when we allow a gas's volume to change, we're also allowing the work to be done either by the gas or on the gas. Okay, so in the first step, we want to get our delta T. And so we can use these equations, these Q, NC, delta T equations. So this will be Q over NC. And now it's just a question of figuring out what is our CP. And what is our CV? So for a diatomic gas, how many degrees of freedom does it have? 5. So our CV is 5/2 times the ideal gas constant. And then to get CP, we just add 1 to that. So it'll be 7/2 times the ideal gas constant. So you can see we don't need to look them up in a table. We just see what kind of gas it is and we get the number. And so you will be expected to know how to do that. Like we may tell you a problem with a gas and you're not given the number for the molar heat capacity, you have to figure it out. Okay, and so we could plug this in and we get 6.8 degrees Celsius or 6.8 Kelvin. And then we can do a very similar thing with this constant volume heat capacity. So this was with CP, this was with CV. And when I plug that in, I get negative 9.6 degrees Celsius, right? This is a heat taken out. 600 joules are removed in the second step. And so overall, when we add heat, we increase the temperature by 6.8 degrees Celsius. And then when we remove heat at a constant volume, the temperature is changing by negative 9.6 degrees Celsius. 1 second here. So yeah, so the overall delta T, so delta T total is 6.8 plus negative 9.6. Which is negative 1.8. And so we didn't actually need to convert in this situation. So we started at 20 degrees Celsius and we end at 17.2 degrees Celsius. So this would be our final temperature. And so it's weird, right? We added the same amount of heat as we took away, but in that first step, where the pressure was held constant, the gas was allowed to change volume. So as we added thermal energy there, when the pressure is held constant, some of that thermal energy is going to go into changing the temperature, but some of it's going to go into expanding the gas, doing work. And so that steals some of the energy that we then have trapped in that volume of gas. So when we hold it constant and take energy away, we're able to get more energy from the temperature. And so we end up with a gas temperature lower than the starting temperature. Yes.
How did you get the final temperature?
Yes. So basically, when we add 600 joules of heat, we increase the temperature by 6.8 degrees Celsius. So at this step, so the sort of midway temperature would be 26.8 degrees Celsius, if I did my addition and subtraction right. And then in the second step, we take 600 joules away, but now we're doing that at a constant volume. So it's a different type of process. We have a different heat capacity. And so here we are subtracting 9.6. And so if we do 26.8 minus 9.6, we get 17.2. So that's the mathematics. You know, understanding it conceptually maybe is a little harder. Yeah.
For the change in total temperature, you put negative 1.8, but it should be -2.
Yes, sorry. Thank you. Thank you. I appreciate the correction. So negative 2.8 degrees Celsius. Very good. Sorry if that's what was contributing to the confusion in this. So this would be an example of a really typical problem that'll be in like next week's homework, basically, of using these gas properties to figure out how temperature changes is related in relation to work and to heat. Okay. And so, yeah, this was just a little bit of an extra slide talking more about how adiabatic processes are a steeper curve in our PV diagram, a more efficient type of thermodynamic process. And you can see these gray curves here are constant temperatures. We call them isotherms. And so we can figure out what temperature these are by thinking about the ideal gas law, PV equals nRT. So these 2 points have the same pressure, but the volume here is larger. So this is at a higher temperature, and this is at a lower temperature. But every point along this curve is going to be at the same temperature. These gray curves are the relationships we get, this sort of P is 1 over V type behavior when we hold the temperature of an ideal gas constant. But by doing some pressure and volume change in an insulated container, like you can see in the top right here, we are following this adiabatic curve, which goes between temperature curves. So you can change the temperature of a system by keeping it insulated and allowing it to do work or to have work done on it, which then all goes into the temperature, right? This delta U equals Q plus W. For an adiabatic process, this is 0. So any work we do on the system will go into changing the temperature, basically. It's an insulated system, so it's also naturally a closed system in that respect. So this is all I really want you to know about adiabats, but it's, like I said, it's just a vocab word that once you've seen it, you'll start to notice it in like a ton of chemistry and biology textbooks and papers and things. So I want you to leave the class aware of what this means. It's just an insulated process, basically. Okay. And then I expect you've probably learned a lot about enthalpy in chemistry, so I'm not going to belabor it too much, but I just wanted to add this diagram and to give you a bit of a physicist context for enthalpy. So this is from my old textbook that I had. So enthalpy, it's not only the energy it takes to make a system, to heat it up, but it's also the energy it takes to push the air out of the way in order for that system to have a place to be. So this is oftentimes in chemistry, I think enthalpy and energy are kind of used interchangeably. You talk about how much enthalpy a reaction produces, and chemists usually basically just mean energy for that sort of situation. But you can imagine if you have a reaction that, goes from a liquid to a gas, so even something as simple as boiling, which isn't a chemical reaction, but is a physical reaction, that the enthalpy and the energy are not the same there, because you're having to do some work to push the air out of the way when you transition from a liquid to a gas. And I think a great example is if a magician wants to make a rabbit appear, not only do they have to give enough energy to make the rabbit, but they also have to make a space for it. They have to give enough energy through their magic process to push the air out of the way, push that 1 atmosphere of air out of that volume V in order for the rabbit to have a place to be. And so that's enthalpy. That's the difference between that and energy. So enthalpy is the energy plus this PV term, which if you have work being done at a constant pressure, 1 atmosphere, then whatever the change in volume is, that's the work required to move that gas out of the way. So this is the critical idea. And you'll just see this. I'm not going to get into this sort of detail, but if you're interested, check out the book section on it. That basically for constant volume processes, if you think about the first law of thermodynamics, if you have a constant volume process, then there's no work. And so in that process, the internal energy and the heat are the same. Whereas if you have a constant pressure process, so this is for constant volume, for constant pressure, it's a little bit more complicated because you do have work and heat. And so you might ask yourself, what is this heat equivalent to? And the answer is the enthalpy, right? So the work here would just be minus PV. And so if we get that over to the other side, we get Q is U plus PV, which is the enthalpy. So depending on the type of process, we can equate the heat that we add or subtract from the system to either the internal energy for a constant volume process or to the enthalpy for a constant pressure process. And then like we saw for an adiabatic process, there Q is 0. So we can just relate the and sorry, this should be delta U, technically speaking. So for an adiabatic process, we just relate the internal energy change to the work done on the gas. So those are sort of the three possibilities. Looking back to the first law of thermodynamics, we can imagine what happens when we have, each of these types of change. What happens to that first law of thermodynamics? How do we think about either what terms are going to 0 or how we can rearrange things and rename things to make our lives a little bit easier? Okay, so that's the end of chapter 12. I don't know why it always wants to do this for me. Let's try it this way. Nothing, huh? Okay. We don't have a ton of time left, but we're going to try to start chapter 13 and the computer is just completely frozen. So maybe this will be the end. There we go. Okay. I've got to share this so it'll be visible. Okay. So because of time, this will run into tomorrow, and then we'll probably just shorten our discussion of entropy a little bit. But chapter 13 is all about connecting microscopic process to the large scale, the macroscopic process. And so everything that we can observe about a gas or any system, it has to be due to the atoms and the molecules, something about their motion or their properties. And so a big task of early thermodynamic study was to figure that out, to figure out how can we go back and forth? How can we take what we know about atoms and molecules from chemistry and apply it to physics? And then how can we do the reverse as well? And so you can see if you have a box of gas, you can think about those gas molecules as bumping into each other, having all these velocities in random directions, where if we increase the temperature, we expect the velocities to generally increase as well. And so what does that distribution of velocities look like? And how can we turn that into physical processes? That's what chapter 13 is all about. So this picture on the left just gives you an example of how we could measure the speed of a gas, because it's kind of a cool experimental question. So what we have is on the left, there's a box of gas. So this is a box of gas at some temperature. And then the rest of this is all evacuated. We've sucked the air out so that there's nothing for the gas molecules to bump into. And what we do is we first only let the gas through a little opening so that we just have a beam of gas, basically, gas traveling in one. So only the gas molecules traveling to the right are able to pass through, and they're all in a pretty concentrated straight line sort of situation. And then what we do is we rotate this wheel around that has some cutouts in it. And so only the gas going at a specific speed such that it can get through both. All right, if it's going too slowly, then it'll not be able to pass through. If it's going too quickly, it won't be able to pass through. And so only a specific speed will manage to get to this detector, where we have some either chemical reaction take place or some little electrical signal that we can count, basically. And so what you do is you sit a grad student, in front of this thing, and you tell them to count all the molecules going each speed, and you make them plot it in a histogram, and you get the picture on the right. So historically, that's exactly what they did. And what you find is that even for a normal temperature, so this is nitrogen, diatomic nitrogen at room temperature, 20 degrees Celsius, the molecules are going incredibly fast, right? You can see that the average molecular speed is in, around 500 meters per second or so. Meters per second to miles per hour is a factor of 2 conversion. So 500 meters per second is around 1,000 miles per hour. So insanely fast. If this were a large scale object, we would say they're going faster than the speed of sound. But of course, sound is a property through the fluid of air. So the air itself can't be going faster than the speed of sound. But it's going, in crazy fast as like a military fighter jet might go on a normal day. And the other thing you notice is that even at a given temperature, not all of the gas molecules are going the same speed. There are some really slow ones. There are some really fast ones, insanely fast ones, but they're kind of clumped together here. And this distribution of speeds has a name. It's called a Boltzmann distribution. Again, named after the same Ludwig Boltzmann. And the cool thing about it is it's really technically a Gaussian or normal distribution, but it's a normal distribution in the velocity vector. And so when we turn that into a distribution in speed, it makes it look a little different. It makes it a little lumpy. So if you take a statistics course, or maybe you already have, you can get some practice turning vector distributions into scalar distributions, and you'll see that a normal distribution in a vector turns into, these are called chi distributions in a scalar, but you don't need to know that. For this class, all you need to know is that it follows this Boltzmann distribution that we're going to talk some more about. But before we do, there's an important property of gases that we might be interested in at the molecular level, which is how far can they travel before they bump into each other on average. And so this is called the mean free path. And so you can imagine there are all these gas molecules, they're bouncing around, bouncing into each other. And so we expect them to not get very far before they hit one of their fellow gas molecules. And it turns out we can actually find how far they go. And all we need to know are the so-called molar density, sometimes called the concentration, the number concentration, which is the number of molecules over the volume. And we need to know R, which is the radius of the gas molecule. And the book says that you can basically use 1 angstrom as an approximate value for these. So for a diatomic molecule, it's going to be very close to an angstrom, which is 10 to the minus 10 meters. For a monatomic molecule, it's going to be closer to 1/2 of an angstrom. So something around that. We would give that to you in the problem. We don't expect you to know that. And so just by plugging those two things in, we can get the mean free path for various gas molecules. And it turns out that these mean free paths are incredibly, incredibly small. So for a typical gas at room temperature, it's maybe 100 nanometers, okay, before they bounce into another gas molecule. And the gas molecules themselves, their radius is only like 1/10 of a nanometer. So basically it would be like, as a person being able to walk like 1,000 like 500 meters before you bounce into someone. So it's a pretty good amount of space from the perspective of the gas molecules, which is why the ideal gas law works. But it's a very short distance compared to any human or biological scale, right? Even cells are much, much bigger than the nanometer scale. And so, yeah, that's what this one is about. This is just, you know, a plug and chug sort of problem. So you might ask, how do I get that molar or that number concentration? And this is where we should talk about the other form of the ideal gas law in the last couple minutes, which is that instead of in RT, which is the number of moles times R, this is equal to N times KB, where KB is just that ideal gas constant over Avogadro's number. So what is something like that, if I remember right? Anyways, definitely not a chemist, unfortunately, but so that's and this KB is known as Boltzmann's constant. So I know there's a lot of Boltzmann running around. So this one from radiative heat transfer is the Stefan Boltzmann constant, named after two physicists, and the KB is Boltzmann's constant, and the distribution of speeds of gases is the Boltzmann, or sometimes called a Maxwell-Boltzmann distribution. So lots of Boltzmanns in this section. But anyway, so we can rearrange this ideal gas law to get N over V is P over KBT. And so they give us the pressure as 1 atmosphere, so that's 10 to the 5th pascals. And then KB is just a constant, and the T we would need to convert to Kelvin, so that's 293 Kelvin. And when we get this all together, it should be around 230 nanometers. So a very small distance scale before the gas molecule on average would bump into one of its neighbors. Okay, so this part mostly a plug and chug, but we just have to get the number concentration from the ideal gas law. And then I think I'm gonna maybe stop here and save this for tomorrow. So tomorrow we'll look at how we can think of the gases' velocities and their change in momentum and turn that into a pressure, and then use that to get a ton of properties that are really handy. But like I said, we'll stop there today.